When we're building a regression model, our goal is always to create a model that will help us predict values of y based on values of x. And y is often called our response variable, and x is called our explanatory variable. Sometimes you'll see dependent and independent variables. This lesson is about something called the coefficient of determination, which is also known as r squared. R squared is a statistic that's calculated as a comparison kind of between two different ways of making predictions for y based on values of x. And it involves a quantification of the variation in sort of the same way we saw with analysis of variance. We create a ratio that indicates what percent of the variation can be explained by the model. And R squared is traditionally a topic that's hard for people to understand, so I'd like to break this down a little bit so you can see what the symbolic representation is all about, but also have more of a conceptual understanding of what we're really talking about when we look at the R squared value. In general, what you'll want to keep in mind is that R squared values close to 0 indicate that our model is not very informative and isn't all that terrific at making predictions for y based on values of x. So in this example I have on the screen, I have an R squared value of 0.36, which is not a good number, and we can kind of see that the green points are not very close to the orange line, which means that there's quite a bit of variation that's not really explained by this model. It's coming from other sources, which we call error, right? We don't know what the other factors are that contribute to the variability in y. Here's an example where we have an R squared value that's much closer to 1. So an R squared value closer to 1 means our model does a much better job of making predictions based on values of x. So I'd like to think about a little scenario that can help you, I think, build the concept here. So let's say I am given a task. I'm asked to estimate or predict a person's age in a town. And let's say this person is a woman in the town. And all I know is the average age of women in the town is, say, 34. So knowing absolutely nothing about this person other than she's a woman in the town, I might guess that her age is 34. That's pretty much my best way of making a reasonable estimate. But what if I'm given some additional information, which is the age of her partner? And what we know is that a person's age is generally related to the age of that person's partner. So if I know that one piece of information, I should be able to better predict the age of the person I'm tasked with guessing. So that's the idea of regression. Does the additional information of this factor help me better predict the response variable? Just some nuts and bolts here. The y bar is representing the average of whatever this variable is. The y hat is representing the model that I've created that takes into account this factor represented by x. Okay, so in statistics we have various sources of variation, and I wanted to break down those sources of variation in a way that I think will make some sense to you. So in your book, you've seen this before in analysis of variance. You see something called SST, sum of squares total, and it's represented with this formula here. Now we could represent this in our graphic by thinking about the differences between each observed y value. So each observed y value is the y value in the pair. So in this case, the y value would be 6, for example, if I'm looking at this particular dot. So sum of squares total measures the overall difference between each observed y value and the mean y value. So that's, we could actually make squares to show that. So if I were to say, okay, here's the difference between an observed y value and the mean y value, I can make a bunch of squares to show this, and then we can get a sense of the overall magnitude of the differences between the observed y values and the mean y values. We're going to have some overlap here, but this is the idea. So this large difference is going to be a big contribution to that overall total. So just in your mind, take a picture with your mind of the overall area that's represented by these squares, and that's going to be the sum of squares total. Okay, so the next term I want to focus on is now called the sum of squares residual, and that looks at the difference between each predicted y value for a given value of x and the mean y value. So a predicted y value is going to be a point on the line that corresponds with the observed x value, and we would get that by plugging in, right? We'd plug in y hat I is equal to whatever the intercept is plus whatever the slope is times that particular x value. So in this case it would be 8, right? And we would get a predicted value of y using the model that we've created. Okay, so we would do that for each of our points and get these predicted y values. So here I'm just kind of looking at where the x value would be for each of the points and then finding the corresponding point on the line. So each of those would be y hat I, right? Each of those. And then I look for the difference between that number and the mean of all the y values. So let me just do some more squares like I did before. No, these go here. All right, and this one doesn't even have a square, it's so small, right? Because the mean and the predicted y are pretty much right on top of each other. So for this one, I'm gonna have this big of a square, and I kind of run out of space. It's tough with the overlap a little bit to see the overall area, but we'll try to do that. Okay, so hopefully I've gotten all of those. So that's the sum of squared residual, or sum of squared regression. I think I've been saying it wrong. Regression sum of squares. Sorry about that. Regression sum of squares is what they say in this book. Now, notice that the regression sum of squares is obviously a smaller number and then the total sum of squares, and that's because there's this additional variation called sum of squared error, and that's the difference between each observed y value and each predicted y value. So that's another source of variation, and that's a source of variation that we haven't accounted for. That's kind of variation that could be due to other factors. It's not explained by our model. So let me go ahead and see if I can represent that. Okay, so what is my sum of squared error going to be? Well, that's going to be the differences between the observed y values and the predicted y values. So each of those is going to have a square. Okay, so not the most gorgeous picture, but at least you can see now this is another source of variation. Okay, so sum of squared error, the one we see right now, is one that we can't account for with our model. the variation that we can explain is the sum of squared regression. And the R-squared value is actually a ratio of the sum of squared regression sum of squares over the total sum of squares. So that's how we get our R-squared value, and it's interpreted as the percent of variation explained by the model. It's usually represented as a percentage. Okay, it could also be calculated by taking 1 minus the sum of squared error divided by the sum of squared total. So it's everything except for the variation that's just random that we haven't been able to explain using the model is another way to think about it. And the R-squared value is actually the correlation squared. So if you knew the value of the correlation, which really has nothing to do with the model, it has more to do with the data. It tells you how closely related, how close the observations are in your scatter plot to sort of a straight line. That value squared will actually give you the correct value for R squared. Okay, so looking at some data, we can see that a model, if we were trying to predict, say, house price from the size, the price of a house from the size of a house, we might create a regression model, and that regression model would have an R-squared value of 0.88. So you would know from that your model is a good model, that 88% of the variation in the housing price is explained by the size of the house. So that's a useful thing to know when you're evaluating how good your model is.